saw the periodic conditions, we saw basically phononic crystals, then we saw how we can simulate radiation losses and how to shield it using the phononic crystals. So this is a pretty much a good package, or let's say good overview of the important things you see in mechanic field. Obviously, we couldn't basically cover all the problems you might face in this community. So please come forward. I mean, I've been asked by a few of you. Some of you I know come with your own questions. So just please, yeah. I mean, if we know how, like we have expertise, we can solve it. But let me. So I want, in this last topic, I want to switch gears a little bit to a kind of a different new topic of like a different type of simulation, different type of physics. As I explained before, so the logic of finite dimensional simulations is the same. What is different? So you have to basically develop this kind of feeling is either equations of motion, boundary condition, and this thing. Apart from that, the rest of the stuff will be the same. So the syntax of the software will be the same. But so I just basically, because we have just only one simulation for this thermal transport, and it's sort of related to mechanics. We thought that it might be a good opportunity to actually include it in today's talk. So, okay, so let me let me start. So the menu of today, it would be basically all of us work with lasers and microwaves, and we know that those have radiation pressure and back action and those sort of stuff, those sorts of effects and forces, but that's not the only force that actually in the game. So when you shine a laser into a dielectric, even if it's a pure basically silicon oxide or silicon nitride, still it has a finite absorption. So a part of that light, a part of the force is radiation pressure, but a part of force is so-called bolometric effect. Basically you shine a light to a cavity like that, actually it's get heated. Because it heats, it expands, so it changes the resonance frequency. So what is radiation pressure? You apply radiation pressure, it exerts force, and it changes the size of the cavity. So you can see these two are very similar, and sometimes you will see basically they are competing against one another. Okay. So basically, heating by laser or microwave tones, it might be an issue in your future research, and I want to just touch upon like how we can deal with this sort of problems, and hopefully we can have a nice exercise session out of it if you have the passion to actually follow. It would be a little bit advanced exercise at the end, but let's go. Okay. And I want to keep my focus on mechanics. So we are not simulating to simulate. So we want to just do stuff related to optomechanics, as is the purpose of this talk. So this morning I talked about the fact that how a stress can induce a strain deformations, how a strain can induce a stress, and then I told you there are ways to insert a stress in the material, and like piezoelectricity. And one of the ways is like wire heating, and then it would be a really nice and interesting, basically exercise to think about it. Like for example, you have a optical cavity, and then you pump it with laser power. That heats, induces a strain. Because of the strain, it changes the resonance, like basically dimension. So it changes the resonance condition. So if your blue shifted or red shifted depends on the basically sign of your in this force, you have different optical powers. So what I want to say is like this is a kind of a feedback loop that actually even can lead to basically cooling or amplification. So what I mean is there is a retardation in this loop, and you can simulate all this chaining COMSOL, and it would be a really good exercise. It actually involves mechanics, optics, some heating, heat transport, like absorption, heat transport, and a feedback loop. So this is where a little bit like advanced, but I want to just focus a little bit between relation of heating and how it can basically induce a strain, for example. Okay. Just to keep the talk's coherence, in the previous talk, it started by introducing what are the equations of motion. For mechanics, we saw that it was a Newtonian equation. And then what are the, so here, the equations of motion is just a diffusion equation. If you have done any course on basically thermal transports, you are familiar with this famous equation. It's a diffusion equation, which is you just need to know the thermal capacitance, density, and thermal conductance, or like the ratio, either the ratio of these two, which is a diffusion constant. And you need to know, obviously, next to these guys, you have a continuity, which I haven't listed here. So the divergence of basically, so heat flow is a J vector. So you know that. And basically, on the other hand, next to this guy, you need to know what is the absorption equation. And for this case, we want to deal with the simplest case. Basically, for us, in the most simplest way, energy that is absorbed at the point x, y, z, it could be anywhere. So when you shine laser light can go through your system, and it hits. It's like OMT heating in the depths. So it's not just on the surface, the heat source. So it could be at any point inside your material x, y, z, which is just the simplest case we can imagine. I mean, you can imagine more complicated stuff. It's just an imaginary part of refractive index times the intensity at that particular point. Obviously, we know that there is a time constant and the materials cannot basically respond infinitely fast, but that's a little bit beyond this talk. So let's just move forward. So basically, in mechanics, I told you what are the parameters that we need to set into, which was Young's modulus and Poisson ratio and density. In this physics, when you're dealing with thermal transport, the parameters of interest are thermal capacitance, thermal conductance, absorption coefficient, if you want to study the laser heating, and well, if you want to see the effect of like basically thermal transport on mechanics, obviously thermal expansion coefficient is a relevant number. Okay. Well, so by that I want to just kind of jump, since we know what the COMSOL is, how does it work, how to set up the model and everything. So I can just directly now jump into what we want to see. So I want to start by like motivating why we actually start doing this sort of simulations, which is a little bit like out of like usual practice of this community. And the problem was like I was involved in this basically this project that we have this nano beam next to this optical cavity, and this optical cavity acts as a really good sensor to measure the displacements of this mechanical beam. And you can use that to ground state, like to cold damp or feedback damp this mechanical oscillator to its motional ground state. The problem is like you need to make a really good measurements of this mechanical oscillator in order to actually cool it further. And it turns out that to make better measurements, you need more and more optical power in this cavity, and that's where the problem starts to appear. So as you start to pump this cavity, so you want to cool this mechanical oscillator, but to do that, you need to put more and more photons in the cavity, and eventually you start to heat this system because of OMT heating. And then, so by that I mean like if you put yourself on the resonance, imagine I'm measuring with weak probe, and then I put another probe on resonance. Practically, it should be no back action, right? It should be radiation pressure of shot noise, but we know that in this scales that's very small. So if you pump on resonance, practically you should see no effect except radiation pressure of shot noise. But what we used to see is like the temperature of this base, which was temperature of this beam, which was measured by another like weak laser, was rising as a function of the power of this thing. So this basically led us to believe that actually our laser is ohmically heating this mechanical oscillator, and the question was like, is it like I wanted to test if this hypothesis is correct. So do I get this, basically this temperature raise like of tens of degrees, makes sense or not? So that's where the whole thing actually started in our lab, but actually 4 years ago. So let's actually do this simulation. It's pretty easy. So what I want to simulate just a beam, doubly clamped beam, with a heating source, optical heating source at the center, which is this cavity. And I want to know, like, basically what is the temperature distribution over this beam as a function of time and as a function of position, and see how much the temperature rise up and down based on this the power, circulating power in this cavity. Okay. So to do that, let's just start doing the simulation. So you can folder, if you go to this folder of laser heating and thermal expansion, you would see a folder, subfolder, which is called beam heating, and then there is a COMSOL model inside which you can open. Oops. Okay. So if you do that, why this example? I want to teach you some other stuff about COMSOL. I mean, that was our purpose from the beginning. Show you some. So here we're gonna basically show how we can do some sources, like user-induced sources, user-defined sources in COMSOL. Okay. So basically the simulation is very similar to tasks you need to do. So you start with COMSOL Wizard, you go to 3D, and then previously from this morning we were talking about the structural mechanics, right? So now we're going to use another package here. So inside the heat transfer, you have a physics study. It's called heat transfer in solids. Okay, use that, and when you actually select that, there are two type of basically studies you can do: stationary or time dependent. And we're going to do both of them. So you all this domain type of simulation, type of FTTD. And how do I parameterize this equation? Is kind of interesting. So obviously you have some parameters for the beam, length, width, thickness. Well, this is like a little bit detailed, but this is the offset between this beam and disk. And the way I want to simulate is like I know the input power to my cavity. I know the finesse of my cavity. So the circulating power would be finesse times input power. So I want to do a realistic simulation, And then going back, so you have this beam next to this cavity, and most of the light is actually circulating in the cavity itself. Just a very tiny fraction of it comes outside in the near field, which this beam actually sits in this near field. So by that I want to say that you have the circulating power, but only a tiny fraction of this circulating power sees this beam. So and then we can show you, but it's a little bit like beyond the topic of this simulation, is that this fraction is in the order of 10 to the minus 3. 10 to the minus 3. So only 0.1% of the optical mode volume sits in this tiny beam. Why? Because first of all, it's outside the basically this cavity, and also it's very tiny, very small. Okay, so that's the ratio of power in the beam compared to the total circulating power. I know the absorption coefficient. I need to know another factor, which is a sampling length and a base temperature of my beam. Which at the time that we were doing interesting in this simulation, we were using doing these measurements at cryo temperature of 5 Kelvin. So the only thing that I need to tell you what is this sampling length. And what is the sampling length? This is a kind of a important figure of merit for this near field systems, is that if you see from the top, I think Sergey had a nice image of it. So you can see this beam is like in the order of, let's say, 50 micron, but not the entire 50 micron of the beam is interacting with the cavity. It's actually only the central part is about 7 micron of this beam sees the near field of this cavity. And this is a parameter is called sampling length. It can be calculated via different simulations, but you need to like kind of believe me at this point that this sampling length, this interaction length of this beam with this cavity is realistically in the order of like, depends on the configuration, between 1-2 micron to the best cases 5-7 micron. So this is the like span of this, so you have this beam, let's say you have this laser and this is the spot size of this laser, so to speak. This would be the same. Okay. So having this in mind is very easy in this case. The geometry is simple. You have basically we have talked about it a lot. So it's just a block. It's a block of the given dimension. I think it was 400 by 60 by like 100 micron, 400 nanometer. The material is silicon nitride. And then if we start this model, you would see instead of structural mechanics, you would have this thing here, which is heat transfer physics. So if we click on this heat transfer, the same that we did for the structural mechanics in this heat listed in my talk. So this is going to be the diffusion equation and obviously continuity. So this is pretty easy, okay. And we parameterize our problem. Again, the same idea we had with mechanics. You can parameterize your material with Poisson ratio or Young's modulus or other ways. Here is the same thing. So you have this choice of using thermal conductivity, thermal and thermal capacitance and density. But there are other ways to do that. For example, you can go basically use the diffusion constants and like thermal relaxation time. These are all kind of equivalent to one another. But normally from the material data sheets, we know these parameters. This is very commonly used in communities. Okay? Okay. So this is all like basically basics. So when you start, all the surfaces are normally thermal isolators unless you actually choose them not to be. So it's like a free boundary condition we had in structural mechanics, nothing serious about it. The only thing here is now different is you need to, so if you want to start with the stationary or time evolution, the initial condition now matters. So in structural mechanics, I told you if you're doing Argand mode solvent, initial condition mean nothing. But if you're doing a stationary, you need an initial condition to get into this in a steady state. And my initial condition is just initial temperature of this beam, which I put it at T0, 5 Kelvin. I basically introduce in my parameters. Then, sorry? Yes.
Why do you only set the initial condition for one interface?
What?
You only set it for the interface.
No, it's not one phase. It's a whole domain.
Oh, it's domain. Sorry.
Yeah. Okay. Then, so similarities. Back in mechanics, we used to have a fixed boundary condition. Here, the boundary conditions that exist in this, the heat transfer basically world is different. For example, if I right click, you can see the examples of boundary condition. For example, boundary condition of temperature. This means that this phase will be always fixed at this particular temperature that you're going to say. And then you have like basically outflow, thermal insulation, and many other things that periodic conditions. I mean, if you have phononic crystal, boundary heat source. If you have a heat source at the boundary which is injecting thermal energy into the system. So what is the case for us? So we have a beam which is connected to two pads. These two pads have a huge thermal connection to the substrate, which is thermalized to your bath. So we can, for all intents and purposes, we can assume that the temperature at these two surfaces is the temperature of the bath. You might start, we can go through this argument whether it's a good assumption or not. And remember, you're the one with the brain. I mean, this guy will just give you some answers. So whether this assumption is a good assumption or a bad assumption is something we need to investigate. But bottom line, believe me, it's a reasonable assumption. It's not so bad. Huh? Okay. Sometimes we can start from like little assumption and then test our assumptions later. So the only thing so far you saw so thermal heat transfer is not much different than mechanical simulations. You have physics, which is diffusion here. You set boundary condition, you set initial condition and everything. The only thing we haven't said, and that's the whole like basically interesting part about it, is like this thermal heat source. Obviously, if we don't have a thermal heat source, it would be a boring equation, just a beam at 5 Kelvin and nothing is happening. Huh? So the interesting part is like how do you induce these heat sources? So I'm going to introduce you to something here that can be also applied in mechanics if you have a mechanical, basically, energy source, like a piezo. Okay. So what is the heat source? First of all, what do I want to do? Again, going back to the equations. So I want to introduce a sort of a heat source that is Gaussian as a function of x inside the beam. So I have a Gaussian profile. That's the best approximation I can find. A Gaussian profile for heat source for the laser lights. Laser light has a Gaussian distribution over the beam, and we know the power, we know the thermal absorption, and then we can calculate the basically we can calculate the thermal transfer. So my goal is to have a Gaussian profile. So this is the beam. I want to have a Gaussian beam, optical beam on top of this beam. This would be very similar if you have like a laser light, like interferometer. It would be the exact same thing. It would be a Gaussian spot on top of a beam, and you want to see how it's hit the beam. Yes.
Can you explain it to me, like with the picture you just showed? What are we doing now? What is moving?
Nothing is moving. So everything is there is no mechanics involved in this simulation. So I just wanna now basically introduce a heat source within this object. So heat source is not a boundary condition. Within this heat source, somewhere at the center, I want to assume that this center is illuminated by Gaussian laser light, and a part of that laser light is absorbed by the material by absorption coefficient.
Can you go back to the PowerPoint where you have this circular resonator? And so it's the resonator that shines light radiation onto the beam.
Yeah.
But the beam is also your mechanical oscillator that's absorbing with another laser.
Yes.
So now we are. What are we modeling now?
So we are modeling just like basically forget about this part. We have a resonators basically pumping on resonance, so we have a circulating power, and that's just illuminate the beams. A part of it will absorb, and I want to see how much the temperature rises. That's it. Very simple, huh? So I have to go faster a little bit. So I want to do something which is weird. So the thermal source is not at the boundary, which is usually the case for the all this thermal transport, which the energy comes from a boundary and leaves. The energy, the heat, basic heat element comes from within. So you have an optical light, you're shining at the center, it forms a Gaussian spot, and a part of it will absorb. So to do that, first of all, I need to define a Gaussian function. And that's how you need to define it here. So if you go to this definition, this is the new part of this simulation. How to define functions in COMSOL. You can do it in MATLAB. If you were using LiveLink, it would have been much easier. But in graphical user interface, if you right-click in this definition, you can actually define many things like variables. You can define functions and other stuff. And in built-in functions, we have some functions that we might use, for example, like as a excitation, maybe as a function of time. For example, you can see, you can have your analytic, your own function, but also you can have some described function like Gaussian, a ramp, a rectangle, a step, a triangle, waveform, random, etc., etc. This will becomes handy later because, for example, you're simulating a mechanical oscillator and you want to know its response to like a ramp or like a delta function. This is how you need to implement it in future. So I'm showing you within this example what are the other features exist also in COMSOL. So you can use this function. So I'm going to just use this, basically Gaussian function, and if you click to the inside of it, you would see I call this function, you can give it a name, GP1 I gave it a name, and obviously the location of it is at center 0, and the standard deviation of this Gaussian, I put it this sampling length, this spot size. Nothing crazy. It's a Gaussian with a spot size of this sampling length. And then using this Gaussian, I make my own function, like one analytical function. I call this function laser power. It's laser power as a function of x. I assume in y direction is uniform, so it's just it's you have only functionality in the length. So in this direction it's uniform. It's only Gaussian in this direction. So what is the expression? Circulating power. So what is? I want to know how much energy is absorbed per unit of actually volume. So circulating power times the fraction of the power that is in the beam, circulating power in the cavity times the fraction of power in the beam, times my Gaussian envelope, okay, and divided by the cross section of this cavity, okay. So I want to know what is, so this is the intensity of this light divided by cross section. Okay, so that's actually basically so in this direction is a Gaussian, and in the other two dimension is uniformly distributed. So the power density with the units of like watt per cubic meter would be this. So everybody agrees? Are you following me, guys? It becomes important right now. So then with this definition, I can go to my thermal heat source, and you can add this thermal heat source, just right click, and then you can choose a heat source. That's how you define a heat source. If you do that, which I did it here, you would find out that such a thing actually will open, Okay. So heat source. What is heat source? So if you open it, first of all, the equation of it is like energy is at the energy which is defined, Q naught, and obviously it's a general source. It's user defined. And how is it actually? How do I calculate the energy absorbed, thermal energy absorbed by this beam? Is just the laser power times absorption coefficient with the units of watt per cubic meter. Yes?
Yeah, to me, the way I understand it, though maybe it's part of your modeling, but this is a surface effect, not a volumic effect.
It's a volume. I mean, the laser penetrates into this volume as it's dielectric. So it's transparent. Well, so if you do this, that's then the model is the model is sort of complete, and you can proceed with the study, right? So you can mesh it, and then you have this, basically a stationary study that I described. Again, same stuff, stationary. So the only thing that I did here, I added a parametric sweep on the input power. So I want to know what is the temperature as a function of input power. How does it raise? Huh? So I've made a parametric sweep. We don't have time for me to run it, but if you run it, you would get this type of answer. Huh? So what is this type of answer? The temperature is color coded right now in this 3D plot, and obviously the brighter regions are hotter than this narrower regions. Huh? So then we can, what we can do, we can, for example, if you want to plot it properly, we can cut a line through this object like this one. We did it before, cut a line through, and then plot the temperature as a function of x to see exactly what's the temperature, basically distribution. And if you do that, again, I'm using what we discussed in sessions before, this is what you get. So that's the temperature gradient, that's the temperature distribution, and different plots here are for different powers. Different curves are different powers. But that's the temperature gradient, so it's practically a rectangular thing. And if you think about it, it's not that crazy. I mean, what is the diffusion equation in 1D? If you imagine your beam is 1D, is just second derivative of your mechanical, your thing at the stationary is a constant. So it gives you just a slope. That's it. I'm sorry, second derivative is 0. And then it gives you just a two linear functions with a maximum at the center. So it's not that crazy. So what else we can do? So for example, we can cut through this line and then plot basically the temperature as a function of the temperature of the center as a function of the input power. That's another thing we can do. For doing that, what you need to do, for example, I made a cut point at the center. So I want to basically plot the temperature of this point at the center as a function of the parameters that I sweep. I'm sorry, not this one. This one. Huh? So power, input power as a function in milliwatt, and this is the temperature. And what we find out is that, well, this makes really a good sense with our measurements. If I show you again what we measured before, was we showed basically up to 40 Kelvin temperature raise from 5 Kelvin. What we simulate is very close to that. Okay, with a linear dependence on the power, obviously. Okay, so that's one thing you can do. But I want to move one step forward and show you one other thing that is important, especially for the exercise. Is that what is the time constant of such an interaction? Obviously, if I start, imagine my laser is off and suddenly I turn on the laser. How long does it take for this beam to actually get to this high temperature? Because I mean, temperature is diffusive. It cannot react instantly. It needs a time to diffuse. Huh? So for doing that, I added a second study, which we haven't seen today. It's the first time. It's a time, and one thing, first of all, you can add multiple studies to one model, no problem. You can simulate them separately. But since we are seeing this time dependent for the first time, it's practically a sweep of time. It starts with the initial condition and it just moves basically the problem further. So what I have done is if you take this study, it will give you a time range. For example, from I simulate from 0 to 500 millisecond with the steps of 6 millisecond. Okay, that's how it just evolve the equations of motion as we go, basically as we go in time. And then if you do that, again, you can calculate the temperature for any given time, right? Obviously, at time 0, the temperature of this thing is at base, huh? And then it starts to basically move up, huh? So for example, you can see, you can animate this thing. Probably I have the animation. No, I don't, unfortunately. But what you can do, again, you can put another like cuts and then plot the temperature of the central point as a function of time. And this is very important because what you see is that temperature starts from the base, and as the time evolves, you raise the temperature, and then eventually you asymptote to this steady state stationary that we actually solve together. So from this, if you plot it in log scale, you can calculate the time scale. That is called like thermal phonon relaxation time. It's the time that it takes one phonon to diffuse out of your system. That's a time scale of this bolometric force. So this sort of simulations that I wanted to show you. So if we do this job, we find out that obviously with power is linear, and this is all at 20 hertz. So time scale of this, frequency scale of this thing is 20 hertz. If you modulate the power faster than 20 hertz, the temperature cannot follow. If it means like you need to like modulate the power slowly for temperature to follow your power modulations. Okay, pretty easy one. But I just wanted to give you a feeling of what are other physics we can do. Also, what is a time trace? If you have any questions, if not, yes.
Is the power fraction parameter used in the simulation, is it assumed, or how can you derive it from other systems?
Power fraction. Well, for our case, we studied that system for years. So simulation can be used. For example, you have a laser interferometer, you have a laser, and you know the spot size. So you can form a double Gaussian, and that would be your intensity. It goes through. Imagine like this thing is transparent, so it goes through, and it can be observed at any point. Okay. So this was one. That's one way. And then there, for example, if you have a Gaussian, if the Gaussian beam is much smaller than your beam, 100% of the light would go through the beam. But if you have a near field interaction, we know that most of the light is in the cavity, a very tiny fraction of it goes through the beam, and we can calculate that via other simulations. Okay? So if there is no more question, I want to conclude with one tiny little like sort of relate to thermal so it's kind of relate mechanics to thermal transport. And this is a notion that I started with. So as I said, I've done my PhD in the business of high stress silicon nitride mechanical resonators, and it's been it's mind boggling. Even after these years, people know this material for actually 15 years. We don't know where the stress comes from still. It's a shame. For example, why? Because it's amorphous material. For gallium arsenide, we know the stress, most of it comes from the lattice mismatch between silicon and gallium arsenide lattices. Here, there is no lattice, and we have some ideas of, the problem is like there's not one source for this high stress. There are different factors that coming into game, and this is one of them. It's called thermal stress. So what's this new in the field? But for those of you who have worked in a clean room, you know that silicon nitride is a material that we put via LPCVD at really high temperature, like 1,000 degrees. So what's the problem? So imagine I put this thin film, like 2 pads and a beam, and raise this temperature up to 1,000 degrees. So in 1,000 degrees, you put there, and then you have basically low pressure chemical vapor deposition. So basically at high temperature you insert silicon gases, and then the silicon nitride will just snow on your silicon wafer. So this is okay. At 1,000 degrees, these two have the same basically volume, not same volume, but same radius in a wafer. The problem starts when you start to cool down. Obviously, you want to take it out of furnace. And fortunately, for my case, because I can do a PhD on it, thermal expansion coefficient of silicon and silicon nitrides are vastly different. So when they cool down, silicon is smaller. So silicon shrinks less than silicon nitride does. Okay? So now think about the relative motion between these two. If I imagine my silicon nitride is not moving, it means that silicon is moving away. So when I start at 1000 degree, these two objects, they have the same length, and when you cool down, if you imagine that silicon nitride is not moving, these pads underneath are moving away. Is that clear for everybody? So when they're moving away, they're pulling this beam with them. And obviously substrate is 500 micron, and this thin film is 100 nanometer, so this substrate has much more power than this guy. Obviously, this thin film tries to resist this motion, but it cannot, because the masses are like basically orders of magnitude different. So these guys win and actually really pull this. So this stress that comes from the thermal expansion coefficient mismatch, it's called thermal stress. And we're going to calculate how much of this stress actually, if you start a wafer at 1000 degree and these two are at equilibrium and we cool it down, we're going to calculate how much stress will that induce into this beam. Okay? Sounds fun, huh? So these values, I take them from Wikipedia. Unfortunately, and you can do the same simulation. For example, Mario came to me like the other day. They were using these drums, aluminum drums, and they were cooling down to like dilution refrigerators. Same thing can happen. So when you change the temperature, and if your substrate and your system have different thermal expansion coefficient, they can either compress or basically pull against each other, depending on the thermal expansion coefficient. Unfortunately, our simulation would be a really vague one, because in reality, thermal expansion coefficient itself is a function of temperature. So it changes by temperature. But I'm just assuming that this is an average value for thermal expansion coefficient over this like 1000 degree basically region. So how do we do that? It turns out actually you can do it via just a mechanical solver itself. So I'm going to set up just a structural mechanics. We did it pre-stress analysis. We done it a bunch of time this morning, so nothing complicated around it. But it gives you an absolutely interesting result. Okay. So my geometry is very simple. I exactly want to simulate what I described. So a beam, two pads sitting on silicon. Obviously, silicon is much thicker than this, huh? And the thing that I choose is structural mechanics, and the rest of it is exactly the same as we saw before. The only difference here is that, remember how we insert thermal stress, initial stress in these films? We would have right-click on this. I said initial stress and strain back then, but now I told you I will come back to this, thermal expansion. This is the way to model thermal expansion in structural mechanics. So if you click on that, you would see this, thermal some number. So the temperature, your final temperature actually, and obviously you need to give it the thermal expansion coefficient, which is actually we get it from the material. And T0 is the starting temperature. So it starts from the T0 and it goes to this final temperature. So it just basically cool down or heat up, depending which is hotter. And then at the same time, it calculates how much stress or how much motion this thing will induce, how much expands. And obviously, because one of our objects have a different thermal expansion than the other, when this thing shrinks and one of them shrinks less than the other, it pulls. So if I do that, actually, if you look at the material, now there are two more. As soon as you activate that, there are two more. One more. One more line here would start to appear, which is this thermal coefficient, thermal expansion coefficient, which I define it as alpha. And I did kind of a, interesting way is that I came here and choose silicon nitride and like basically name this silicon, which is a very convenient way. So every time that I call silicon, this entire block would be activated. Every time I call silicon nitride, entire this block, instead of just choosing it every single time. And what I did is actually practically just basically give two different values for thermal expansion coefficient of these two matrices, which actually I found it online. Huh? And then again, fixed boundary conditions of like basically a few points. And by doing that, we can do a pre-stress analysis, a stationary solution and argon mode. So in a stationary solution, is gonna basically relax this temperature, calculate how much expansion you get, and calculate the stress, and use that as a basically that stress profile as the initial condition for this argon mode solver. And if you do that, the result will be amazing. So this is the thermal expansion. This is the stress profile, color coded. So here I'm showing in the color coding one minus stress. I told you this is a scalar value for the stress tensor, and so you can see here nicely that basically, obviously the stress in silicon nitride thin film is obvious, huh? It's different color is here. Is different than the blue, which is 0 for silicon. And if you calculate that, you can again go there and then calculate how much stress you would get. And if you can, and you can also check that your frequency is like a double clamp beam, higher frequency. This is easy. But what I want to emphasize is that by doing such a thing, you can get a stress of about 500 megapascal. So the stress with this technique, if you calculate this, the stress you get, you can just read it off this plot, it's about 500 megapascal. And you might ask me like where the rest of the stress comes from. And my answer is I don't know. As far as I know, nobody knows exactly. Nobody knows in a sense that we have some ideas, but I haven't seen any serious work that can calculate 1 gigapascal stress. Huh? Well, so by that I kind of conclude the session of today. Let me just also tell you what I want you to simulate for the from one of our basically previous PhD students in the group of Tobias Kippenberg, Albert Schließer. It's actually from his thesis I took it. Now he's a professor. I mean he has his own group. So what is this? So this is a response of a bolometric, so-called bolometric response of a WGM resonator. And I also put some initial files for you, but if you can simulate such a thing, it's absolutely interesting for a carrier. So you have a WGM resonators, and we know that the light is basically circulating inside this, inside this peripheral of this circumference of this cavity. Obviously, you can see it would heat up, and then you can use this temperature now. You learn how to use the temperature to calculate thermal expansion. Huh? So now the next you can calculate is the force. So what is this measurements? Basically, they put a laser on resonance, and then they try to modulate the power of this laser. As I just described, at very low frequencies, the temperature can basically track your power modulation. So you can see you have a flat response, and then you have a knee point, you have a pole here, it's like a filter. So as your modulation frequency increases to few hundreds of Kelvin, few hundreds of kilohertz, actually your response cut off. So this is so-called the bolometric force, and what I want you to calculate is like what is this time constant for bolometric force. And it's very important, guys. This is really absolutely important for you who are starting in this field. This force, if you continue on resonance, on mechanical resonance, you have back action, radiation pressure. And if this time constant is high enough, so this bolometric force is not too small, these two forces would actually interfere with each other. So in early days, in like 2013 to 2003, 2002, you saw a lot of papers declaiming radiation pressure, but none of them were actually, if you look at the radiation pressure, but actually bolometric forces. And this is something that in your system designs you need to take care of it. That basically you don't have much of bolometric forces at the frequency of your interest. For example, in this particular cavity, so the cavity of interest was at, let's say, 10 to the 8, so it's 100 megahertz, and then bolometric force cutoff was at 100 hertz. But you can see the response of these two are 3 order of magnitude. So not only you need to be above this line, above this bolometric forces, but also you need to be much higher frequency, or these ones needs to be much lower frequency, so it has time or like space to basically be damped, and then you have a pure radiation pressure. Okay, this is something that all of you have to do if you're working with optomechanical system. Make sure that the effect that you're seeing is radiation pressure, not bolometric. And you can get a sense of time scales here with this type of simulations. Okay, so with that, is there any questions? What? Coffee? Exercise? I didn't hear. What was that? Yeah. So with that, actually, I conclude. So we can have a coffee break now, and then we come back for the exercise session. There won't be any presentation, but me, Mohammed, Sergey will be around, and then you can, because I gave you a lot of exercise today, you can choose the one actually interests you the most. And I absolutely recommend that you go step by step. I mean, you saw me doing it. It's different than you do it step. So when you do it, you start to see, you cannot do it actually, and then you start to learn by experience. Okay, so yeah, thank you for your attention.